Good afternoon, ladies and Justin. Good to have you here today. What we're going to be doing is going over these exercises, which are practical, real-world uses of vectors. So we have navigation. An airplane is flying on a bearing of 335 degrees at 530 miles per hour. Now, what happens in the vocabulary of bearing? What happens is bearings are done in something called azimuth, where north is defined to be 0 degrees, and then going around clockwise, you get to 90, 180, 270, and 360. But for the purposes of this class, so as to not be too confused, I hope, what I want to do is I want to just stick to our standard position. So our standard position is going to be in this kind of arrangement. Does everybody see the directions I'm drawing here, representing by the capital letters?
Yes.
Does that make sense? Okay. So what we're going to do is, I want to, for purposes of continuity, to stick with our standard position angle format instead of the azimuth one. And so if we have an airplane flying on a bearing of 335 degrees at 530 miles per hour, what happens is 360 is over here, so 335 degrees is going to be approximately over here. So here's our 335 degrees, like this. And we want to break that down into component form. And we have, in our vector, it's going to represent the speed. So our vector, we would say, has a magnitude of 530 miles per hour. That's how we would do that. And I'm going to go ahead and erase over here to leave a little bit of room on the left side. So our component form of the vector is going to be R, and R is going to be 530, and that's going to be our radius, essentially. And then we're going to have cosine, 335 degrees, comma, 530 sine, 335 degrees. And then we can use those to get a numerical description of those. So 530, okay, we're in radians here. Let's get into degrees. So we have 530 cosine 335 degrees, and so we're going to get 480.343. So 480, here we go, 480.343. And then we're going to go ahead and take the sine. So 530 sine 335. So we get negative 223.988, right? And that, ladies and Justin, will be our answer to problem number 41. Does that make sense?
Yeah.
Okay, again, it's our cosine is x, and our sine is y. What happened is I had a follow-up question yesterday in 6th period. They said, well, what is R? Well, R is going to be our magnitude. or the radius of the vector. So go ahead and do number 42. I'm going to call somebody to help with 42. And very shortly. Do you feel this connects pretty well with what we've been doing in the class? Right here, it should. And even for the people who were gone yesterday for great humanitarian purposes, I must say. Donating blood to save lives. I applaud you all who sacrificed for that. Okay, let's see here. We have, let's go in. I want to go ahead and turn the sound off by plugging it. Okay, Becky, you are drawing the short straw on this guy right here. So Becky, let me go ahead and erase this sixth period. All right, Becky, number 42. What do you think?
It's going to be 460 cosine 170.
So 460 cosine 170 degrees. Cosine, let me write, if I can do that right, be 460 cosine, man, I said cosine, but right, cosine of 170 degrees. And then this other one's going to be 460 sine 170 degrees. Okay, so that's going to be equal to
Negative 453.02.
452.02.
Yeah.
53.02,
53.
okay. 453.02. 79.878.
Yeah.
Okay, and then one thing I like to do also is just kind of look at, see if these numbers make sense. So 170 degrees is in which quadrant? Second quadrant, right? The second quadrant is going to have x negative and y positive. Does that make sense? And then to kind of look at the numbers, right? 170 is going to be kind of close to 180. So you know you're going to be kind of close to the x-axis. So you know this negative number is going to be quite a bit bigger than this positive number over here. So just kind of think, because those clues can help you to figure out, maybe I did something wrong, or maybe I'm in radians or something like that. Because do you think that happens a lot? Yeah, it does. Okay, then we get to problem 43. And problem 44 is very much like 43. What that is. Well, we have a class video from yesterday, it was from this class, so.
This one was from a few days ago.
Okay. Let's go to 43. Okay, in 43, what you have is, you have a situation where you have a airplane flying on a compass heading, bearing at 340 degrees. Again, we're not going to use the real compass heading, what I showed you earlier. We're going to just stay off our standard position type of a notation. And then at 325 miles per hour, the wind is blowing with the bearing of 320 degrees at 40 miles per hour. So let's go ahead and draw a little picture of what that is. So we have we have a plane that's flying at a bearing of 340 degrees. So it's going to be about here like this. And we're flying at 325 miles per hour. And it's going to be this thing right here. That is our 340 degrees. Okay, and then we have this other thing here. The wind is blowing with a bearing of 320 degrees at 40 miles per hour. So what I'm going to do is I'm going to draw, maybe not to scale, but just so we can see what's going on here. This vector here, we will say this is going to be 40 miles per hour, and it's going to be at a direction of, I'll have it like this. So this is going to be 320 degrees. All right, so what we have is, essentially we have two vectors out of this. We have 325 r cosine of 340 degrees, and we have comma 325 cosine, sine 340 degrees. Okay, and for this other vector, which represents the wind direction, the wind in a certain direction, we have 40 cosine of 320 degrees. And over here we have 40 sine 340 degrees. And so what we can, pardon me?
That one should be 120, the second one. For 40 side.
Oh,
Down?
this should be 320 here?
No, down. Yes.
Oh, that should be 320 here. Okay, thanks for catching that. Yeah, that's one thing that you go through here. It's easy to not get things right. So what we're going to do is we're going to add these together, and we're going to get a single vector, which is going to be the sum of these two vectors. So going right here, we have 340 cosine of 340 degrees plus 40 cosine 320 degrees. Right, so this is what we have here. So that's going to be 350.137. And then we have over here, if we did that right, and in the calculator, it have to keep track of that, because you can just put 340 sine of, no, I'm lying to you, aren't I? No, that's right, 340 sine, 340 degrees, is that right? Those are the same numbers. Oh, 325. 325, okay, let me just do this here. So you should have 325 cosine, so I got to fix that. 325 cosine 340 degrees plus 40 cosine 320 degrees. There we go. So we have that, so 336.042. And then we have the next one, 325 sine 340 degrees, plus 40 cosine 320, 40 sine 320 degrees. And that should be right. Wait a second. Yeah, that's right. So we get negative 136.868. So this is going to be our answer to part A, which is our component form of velocity of airplane. Does that make sense? Okay. And really you can see that the vector is going to be kind of in the same direction. You're going out this way and so forth. Okay. Next, find the actual ground speed and direction of the airplane. How are you going to find the actual ground speed? Okay, it's going to be this. It's going to be magnitude. That is the magnitude. So we have the magnitude of, we're going to have 336.042 squared plus, parentheses. I'm going to go ahead and just paste this in here by going to second ANS, and I'm going to parenthesize that off and press squared. And so here's our actual ground speed, 362.846 miles per hour. And what is our direction going to be? Well, direction is going to be the inverse tan of negative 136, right? 0.868 over 336.042. And what kind of adjustment do we have to make? Plus 360, thank you, Fran. And so we're going to get our direction. So we put in our inverse tangent of so we'll have, that's going to be our opposite over adjacent, right? 136. 136.8. Oops, yeah, thank you. Thanks for catching that. Okay, inverse tangent. There we go. Inverse tangent of negative 136.868. Over 336.042. And we know we're going to have to add 360 to that. And what angle should we get? Well, it's 337.839 degrees, right? Now let's see if that makes sense. So this one right here is 340. This red one here, this purple one here is 320. And so does it make sense that the real direction, owing to the influence of the wind, is going to be somewhere between these two? Yeah, it does. So we have ground speed, direction, component form, we have everything. So what I want you to do is problem 44, which is identical looking problem. But to me, as you see me do in this one, kind of muddling my way through this one and helping me out, is It's staying organized, really. But if you can stay organized, this is not that hard a problem, is it? No. Any questions on this one? Okay. All right, so I know it looks like Jana's ready, and is everybody else pretty close to being ready?
I'm still working.
I'll give you another minute or so. I'll call somebody. Okay, let's go here. So we have spin. It's gonna go, Jana, it's you. All right, Jana's gonna call. All right, Jana, what do we got here? For part A, okay. So for part A, you got
Okay, I got negative 528.187.
528.187, okay. Let's just pause and see if that makes sense, okay? Now we're going at 170, so it's gonna be blowing over to the left, right? So that's probably makes sense. And this one is blowing that direction too, and they kind of add together. Okay, so that sounds good. Okay, what next?
Well, we need to figure out two different things.
For the second part?
What you said. 170. Oh, okay. I see what I did wrong. But the second one is 52.517.
52.517. Okay. And you just use the same one as same type of procedure as on problem 43, right? Okay, good. Any questions about that? And the vector probably does kind of make sense. All right, go ahead. So you have part B now?
And then first, I got 530.719 miles per hour.
So 530? 530?
Yeah,
0.791 miles per hour. Okay, that's our ground speed. And our direction?
It's 174.322.
174?
322
degrees. And let's see if that makes sense, because it's going to be probably somewhere between 170 and 200, right? That's going to be closer to that 170 than to the 200. So these look like reasonable answers to me. Is that right? Okay. Is everybody else able to follow along pretty well? Elizabeth, you're doing pretty well on this?
You see, I had it until I got to direction, and I don't know what I messed up.
Okay, what you'll have is your theta is going to be equal to inverse tangent of this over this.
Okay, that's where I went off. I did inverse sine. So why was the last one inverse sine, but this one's inverse?
No, what it is I clicked the wrong button when I was up here, but somebody corrected me.
Oh, so it's always going to be inverse.
It's going to be inverse tangent.
Okay.
Now, you could use inverse sine,
But you have to switch.
but then you'd have to use magnitude instead.
Yeah.
Okay, so 187. And you're going to have to add, you have to add 180 degrees
Okay.
here, because we know we're in quadrant 2. And so that's how you got it right, Jana?
Yeah.
Right like this? Okay, did that answer your question?
Yes, it does.
Very good, that's a good question. All right. Let me kind of see where we are on this, because we don't have a whole lot of time left.
So if you're in, I forgot what the charging labels are, but if you're in the second quadrant, you're adding 180, and if you're in the, what quadrant were you in?
We were in quadrant 4.
So for quadrant 4, you're adding 360.
Yes, yeah. Quadrant 4, you add 360. In quadrants 2 and 3, you could add 180. And then quadrant 1, you add nothing. Very good job, Justin. Justin paying attention in class. Okay, we have, for this one here, we have a basketball being shot at a 70-degree angle from the horizontal at an initial speed of 10 meters per second. So what it is, your basketball is being shot at this angle 70 degrees at a magnitude of, I'll just put it in language, 10 meters per second. And then you find the component, and eventually what it's going to do is the thing is going to go like this, of course, right? But what we're talking about is the initial angle. So I will choose somebody else for this. We'll probably just get through 45 today. There's a lot on these. I mean, so much I couldn't get them on a front back, could I? I had to give 3 pages of them. Okay, let's see here. All right. We have for this one, Elizabeth. All right, Elizabeth. What do we have here?
I set it up and it's 10 cosine 70 degrees. So 10, so like this, 10 cosine 70 degrees. And then comma 10 sine 70 degrees.
10 sine 70 degrees. And that's going to be equal to
3.420.
420, okay.
And 9.396.
9.396. And it says, writing to learn, give an interpretation of the horizontal and vertical components of velocity. Did you figure that out? Okay. This is your horizontal velocity. And this right here is going to be your vertical velocity. So, right here, we have the basketball, right? It's deflated. But when you shoot it up, initially, at that angle, the horizontal component of that velocity for shots launched at that angle is going to be 3.42 meters per second. And vertical velocity is going to be 9.396 meters per second up. Does that make sense? So you got like a vector going this way of this meters per second, and then a vector going up this way, and you put them all together. If we recombine them the way we've been doing, or you're going to come back to this thing right here. All right. So we can just leave it there today. Thank everybody for participating, taking your turn.
Well, they won't